Good afternoon, everybody. Tonight we're going to continue with our geometry investigation. We're going to be talking about congruent and similar polygons. So if you'll open your notes, we'll get started. Congruent and similar figures. Well, congruent is a very special term used in geometry to discuss figures that have a correspondence between angles and sides such that corresponding angles are congruent and corresponding sides are congruent. What we mean is A corresponds to D, C corresponds to F, such that A is congruent to D and C is congruent to F. So the symbol is this little equals with the tilde on top, and it's a very strong statement. If I see this particular statement, it's telling me I know for sure that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F. Look especially at this, we call this a statement. A is in the same position as D. B is in the same position as E, and C is in the same position as F. Therefore, we also know that AB is congruent to DE, and we use the little hat on the DE to designate that that is a segment. CA would then be congruent to, it's like a puzzle, FD, and BC would be congruent to EF. Notice that we're mentioning these letters in the same order, and we're very careful about that. We could write that triangle FED is congruent to, you have to be careful with the order because F corresponds to C, E corresponds to B, and D corresponds to F. So I would have to write triangle CBA here. I could write that CAB is then congruent to, think of what you might put there, triangle FDE. So as you can see, the order matters and it makes a difference. I cannot write that triangle ABC is congruent to triangle FED. That is not true because angle A is not congruent to angle F, or it is not known to be so. The only time it would be so is if that triangle were a special kind of triangle. Can you think of what it might be? If it were an equilateral and equiangular triangle, order would not matter. That's a very special circumstance, however. Okay, so now they're giving us a problem, and they're telling us that triangle XYZ is congruent to triangle RST. So to find the values of A and B, if the measure of angle S is 48 degrees, T is 62 degrees, and X is 70 degrees. I know that as the measure of angle Y, well, which angle is angle Y congruent to? It's congruent to angle S. So I can then set up an equation. Don't you just love algebra? And that equals 48. Why don't you go ahead and set up your two equations and solve for A and B? So if you're back with me, hopefully you got A is equal to 13 and coincidentally B is equal to 13 also. Now we're going to bring back something that we just recently talked about as we move on to similar polygons. Similar polygons are polygons that have the same shape but not necessarily the same size. The symbol for similar is just the tilde. So they could be an enlarged or shrunken version of the same figure. They could in fact be the same figure. In other words, congruent polygons are similar. Similar polygons may or may not be congruent. If two polygons are similar, corresponding angles are congruent. So that part of it stays the same. Corresponding sides, however, they are proportional. This is a great reminder, review, and application of our proportions unit. They're telling us in the example that QRS is similar to ABC. That tells me those angles are congruent in that order. So angle Q, and I'm going to put this little tilde here because it does matter, is congruent to angle A. Angle R is congruent to angle B, and angle S is congruent to angle C. Corresponding sides. Notice that this is not a congruent or equal symbol. It's just saying that it corresponds to the other side. So RS would correspond to BC. SQ would correspond to CA. And notice that they are all in the same ratio. In other words, it is maintained that SQ is to CA as RS is to BC. And that ratio in this case is 2 to 1. They're all in the same ratio. All the sides have to be in the same ratio. So if the sides are in proportion, altitudes and perimeters will also be in that ratio. And what do we call that ratio? Other than just the ratio between the triangles, the ratio of proportionality. It can also be known as the ratio of similitude. So you see that similitude, you think similar. And so then we can go ahead and we can solve problems related to similar polygons. If we look at the example, they're telling us that KLMN is similar to WXYZ, and so I know that KN corresponds to WZ. Well, KN is 8, WZ is 6. MN, I don't know what MN is, but I know that the ratio of MN to YZ has to be the same as 8 to 6. So I could just cross multiply there and solve, or I could reduce and use equivalent equations, and either way we should get MN is 20 units, whatever that is. Let's look at the following example. Tell whether the polygons are similar. Remember, their angles have to be congruent and sides have to be proportional. Try those three and come back and check with me. In the first case, they are, because every angle is marked that they're the same, and the sides, it's equilateral, and this is also equilateral, and they're in the same ratio. So this would be true. This is not true because one is a rectangle and one is a square, and this rectangle is not an equilateral rectangle, so therefore it is not proportional. And in the third one, all squares are proportional. Find x in each of the following similar polygons. Write the proportion first. So what they mean by that is basically saying, I want to write the small to the large, or you could do large to small, and my proportion is going to be 6 is to 10 as 15 is to x. I will leave those three for you. I will tell you to be very careful in number 3. Really think about that one and try it on your own and come back and check. Okay, in the first case, we get x equal to 25. Hopefully you solved that. In the second one, my proportion looked like 6 is to 9 because I wanted to do small to large, but you could have done 9 to 6 as long as you did 12 to x. I did x to 12, and I got x equals 8. In the last problem, these are two triangles. I have a triangle here with a side of 24 and 14. The larger triangle actually has a side length of 21 and another side of x. So if you did not think about them in that context, why don't you pause again here and try it on your own. You have to be very careful with nested triangles. This side length of 14 actually corresponds to a side length of 21, and that is as 24 is to x, and you should get x equal to 36. Let's move on. A couple more problems. These problems are used in all kinds of geometry and math, the shadow problems. Remember I promised you would see shadow problems? Well, here they are. And they're based on right triangles. So we're looking at the Transco Tower in Houston, Texas, which is 64 stories high. To estimate its height, you measure its shadow. Its shadow is 55 meters. A nearby flagpole has a shadow of 10 meters. We know the flagpole is 50 meters high. So if you think about this, it's like a right triangle. I have a 50 here, a 10 here, and I have a similar figure because the sun is in the same place in the sky for both of these, and it's casting that shadow. So this is 55 and this would be x. After seeing that picture, why don't you go ahead and solve that on your own? If you're back with me, I got 275 meters high, and that is a very classic application of ratios and proportions that you're likely to see. The next question asks if they are similar, and if so, what is the rate of proportionality? I need to check every side, and they're asking me if DE to PQ is the same as EF to QR, and that would have to be the same as DF to PR. You need to check all three sides and make sure that they are in the same proportion. So go ahead and do that. I checked all three sides. I got 5 to 6 for each side so I know those triangles are in fact proportional. The ratio of proportionality then would be 5 to 6. So that's it. Piece of cake, right? Great job tonight. We'll practice more tomorrow. See you then.